this week I'll start talking about this new chapter 26 and DC circuits. So the reading assignments are this. I think there could be some new concepts, but you should sit down and read. You don't have to read everything in the chapter, just 5 sections, and these are the problems hopefully we can solve. So, okay, maybe we can just take a look at what we did so far. So far, we talked about some electric fields, and we know how to find electric fields. And then we introduced capacitance, dielectrics, and electric energy storage. Like capacitance was like a member of like a circuit that we could utilize. And last week, we introduced electric current and resistance. And the logical next step is to combine these two things, right? How can you combine the capacitors and resistors in a circuit? So let me start. First, we have to have a circuit and we have to have current. For that, we have to have a source that can generate current. And this we generally call EMF for some historical reason, electromotive force. And EMF, which we show with this weird symbol, is the source that provides the current in a circuit. And the thing is, like, the EMF is something like this. You can think of like a gigantic battery with some like terminals, or like with some connection ports. And for any battery, there's like an internal resistance, right? And for that, we need to define a more useful voltage, which we call terminal voltage. It is defined by like this A and B. If these are the 2 ports, the terminal voltage between A and B is given by this EMF minus whatever the current is flowing times resistance. Okay. So that's the definition of terminal voltage for a given current I. So this thing is minus, but if we were, for example, charging the battery, the flow would be in the opposite direction. So we would have this thing plus. Simple. So, but so this is what it is, but I want to point out, unless otherwise stated, we generally neglect this internal resistance because it's generally smaller than everything else in the circuit. And we generally think of this E to be like the terminal voltage. But if the question is explicitly saying that this is the internal resistance, we have to consider this. So now we have the battery, we have the resistor, we have the capacitance. Maybe we can introduce some notation for the circuits. So let's just look at this. So in a circuit, this symbol, like 2 lines, one shorter than the other, we call it the battery. And generally, the side that's like longer is the higher voltage, right? So if you jump this way, you are going from a lower voltage to higher voltage. Or if you jump this way, you are going from the lower voltage to higher voltage. So the capacitor, you know the capacitor, it's these 2 parallel lines of equal length. Some references can show this notation, so don't be confused. And the resistor is like this zigzag line. If we have like a straight wire without anything on it, that means a wire with negligible resistance. Like almost like you can think of this like a wire with 0 resistance. So this thing is like a switch. In some cases, it's like going to be open like this, but in some cases, it's going to be shown like with closed form. And finally, you can have like a ground in circuit. You may have to ground some part of circuit. Sometimes people use this notation. Sometimes people use this upside down triangle. Okay. Maybe we can start with like a warm-up exercise. Here is the first example from your book. So a 65 ohm resistor is connected to the terminals of a battery whose EMF is 12.0 volt and whose internal resistance is 0.5 ohm. Here's the figure. And we'd like to calculate the current in the circuit, and B, the terminal voltage of the battery, VAB, and C, the power dissipated in the resistor and in the battery's internal resistor or resistance R. Maybe I can go ahead and start. So we said, okay, let's start with A. So we need to think of this voltage between these two ports. It is given by this terminal voltage, which is E minus some current times internal resistance. This thing should be equal to current in the circuit, whatever it is, times R. Okay, here E is given, R is given, R is given. The only unknown is I. And I can solve this for I. I is equal to EMF divided by R plus R, which is equal to, let's calculate this. So that's clear, 12 divided by 65 plus 0.5 is equal to 0.18 ampere. Okay, and B, the terminal voltage of the battery, B, VAB is equal to, we just defined it, E minus I times R, which is equal to 12.0 minus 0.18 times 0.5, something like 11.9 volt. And C, power dissipated in the resistor R and in the battery's internal resistance. C, power is, does anybody remember what power was in a circuit with resistor? Good. So I'll use I squared times R. This is going to be equal to, this is equal to 2.1 watt. And this is the resistor. And P, okay. Let me call this P. Battery is also I squared times. Now this little r, which should be equal to 0.04. Okay. But I think in this case, they are like explicitly asking the power in this element and power in this element. And R is already known. I think I just use the current. Of course, you can calculate the V here and the V here, and it's going to give the same thing. That's correct. So now let's think about multiple resistors in a circuit. So like I think we did this thing before with capacitors, and we can do the same thing with the resistors. Like suppose I have two different arrangements. In one, the series are like connected one after another, and we call it series in, I mean, resistors in series. Or we can think of like this arrangement in which like the resistors are in parallel. So let's look at this. So a current here, I, is the same as I, and the same as I, and the same as I, right? So for the given current, I can calculate the voltage difference here, and the here, and then here. But if I sum these three things up, it should be equal to this. So let me write this. So V, which is equal to I times R1 plus I times R2 plus I times R3. But this V, I can like replace this whole thing with some single resistor like that has the same current and the same voltage. And I call it like R equivalent. This is going to be equal to I times R1 plus R2 plus R3. And from here you can see that like equivalent resistance for like its series connection is like just sum, algebraic sum like this. Now let's look at this guy. Here I have some, let's call I1, I2, and I3. Now the sum should be like the current is sum of these individual currents, 2 plus I3. Like here it was like V1 plus V2 plus V3. Here I1 plus I2 plus I3. And from here I can just calculate. So I want to say this, if I replace this whole thing with some single R equivalent, the current will be V over R, the same V divided by R equivalent, and this should be equal to, we know V here is the same as V here, same as V here, same as here. That's the nice thing about parallel connections. So this is going to be V over R, R1 plus V over 2 plus V over R3. From here you can see R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 to the minus 1. Okay. Simple stuff. So let's solve an exercise and see how this thing works. These are example 4 and 5 from your book. So the problem is given like some circuit. How much current is drawn from the battery in this figure? Okay, there are like resistors 1, 2, 3. So let's see the current. And the next question is asking current in one branch. What is the current through 500 ohm, like this guy, resistor? So I can find R equal. First, I need to do this guy, starting from the innermost connection. And I know this is equal to, these are parallel connections. R is equal to what? Okay, if it's 1 over R1 plus 1 over R2, okay, R1, R2, the minus 1, this should be equal to R1 plus R2 divided by R1, R2 to the minus 1. So this is equal to R1, R2 divided by R1 plus R2. So let me just calculate this is and put in there 291.6, 291, maybe that's good enough. And this next one is just algebraic sum. So this is 691 ohm. So from here I can calculate the current. Let me clean this up. The current is voltage divided by R equivalent, and this will be equal to 12.0 divided by 691.6, right? And if I do this, it's like 0.017, it's like 17 milliampere. Okay. And so what is the current through 500 ohm, like this guy? So now I know, let's call this I1 times 500. This should be equal to I2 times 700. And I also know the sum of I1 and I2 should be equal to 17 milliampere. So I1 plus I2 is equal to 17 milliampere. So maybe I can just eliminate one of them. Which one do I need? So I1, I2. They're asking for I1. So let's eliminate I2. So I1 times 500 is equal to 17 times 10 to minus 3. So this is minus I1 times 700. So this is like I1 times 1200 is equal to, okay, it's 11.9. 9 times, okay, that's it. So I1 is equal to this divided by 1200, something like 9 milliampere. Okay, so this is 5, this is 6. Of course, I might have messed up these numbers. You should let me know if you find something different. Let's look at another one. So a 9-volt battery whose internal resistance R is like 0.50 ohm is connected in this circuit shown here, this guy. And the question is how much current is drawn from the battery again. And B, what is the terminal voltage of the battery? And C, what is the current in 6 ohm resistor? What's the current on this guy? Okay, we have to do some stuff. So let me just go ahead and start here. So first I'll find this guy. And I think we can immediately do this thing here, right? Just multiply them and then divide by their sum. So clear 8 times 4 divided by 12. This is equal to 2.6. And this guy is like that, 8.6. And this guy like that is, okay, 8.6 times 10 divided by 18.6 is equal to 4.6. And so now I can put it, okay, maybe all of them together, A, are equivalent is equal to what? 9.6 ohm, and E minus I times R should be equal to R equivalent times R. From this, I is equal to E divided by R equivalent plus R, which is equal to like 0.89, something like 0.9 ampere. Good. So B, what is the terminal voltage of the battery? This is easy. VAB is equal to EMF minus I times R. This is equal to 8.5, 8.6 volt. And C, what is the current in 6 ohm resistor? What is the current here, right? So now I think thankfully I kept these numbers here so I can do this from there. So I1 plus I2, let's call them I1, I2 is equal to total current, which is 0.9 ampere. And I1 times 10 should be equal to I2 times 8.6. Then I can eliminate, which one? I can eliminate I1. So I1 is equal to 0.86 times I2. Let me put this in the other one. 0.86 plus 1 times I2 is equal to 0.9 ampere. So I2 is equal to something like what, 48.48. So you can kind of see this thing is a little bit getting out of control, right? They're like, it's like hard to keep track of the things. So we actually have some useful tricks for this, and let me introduce that to you. And I think you probably know that these are called Kirchhoff rules, okay? These are very useful, and there are just 2 of them. So I want to call the first one, first rule of Kirchhoff, the junction rule. And what it says is simple. If you have like a junction, like, I don't know, something like that, something like this, here, junction. like multiple wires come together. That's what the junction is. And the first Kirchhoff rule says that I in is I out. What this means is all the currents in should be equal to currents out, right? That's actually what we used here, right? We used this one was in, these two are out, so they were equal. This is like conservation of current. So at any junction, the total current should be conserved. Because the charges, when they come to a junction like this, they don't disappear. They cannot disappear. So you better have this rule. And the second, okay, I said Kirchhoff has two rules. One is the junction rule, and the other is loop rule, which I call. And the loop rule is if you make a loop and some of all voltages, like this, for example, this is a loop, this is another loop, and I can add these voltages up one by one, or I can have this other loop, right? I can add every element one by one, calculates potential and add it. So the second Kirchhoff rule says that total voltage you calculate in a loop should be 0. So maybe I can solve this example. It says that calculate currents I1, I2, and I3 in 3 branches of the circuit shown in here, this figure. So I suggest you try to do this way, and then you'll appreciate Kirchhoff rules. Okay, I will solve this with Kirchhoff rules. So let's just try to set it up. So first, the junction rule, there's like a junction here, and there's like I1, there's I3, and there's I2, right? I3 is coming in, and it's going to 2 branches. So what this means is I1 plus I2 should be equal to I3. So this is first. The second is like, let's form some loops. Like, for example, we can go through this loop and follow the current. So the first one, I1, when I flow through this resistor, I'm going to have some I1 times 30, and then I'll pass it, come here, and then come here. There's like a battery, and the voltage is higher to lower, so it's going to be plus 45, and then I have another current which is going to be equal to 1 times I3, and there's another one which is 40 times, let's combine these two guys, it's like 41 times I3, and I am back to where I started, so it's going to be 0. So this is loop number 1. So the other loop is, maybe I can go through here. Let's do this. So again, I start from, let's go this direction. I start from 45, okay, 45 minus, okay, this one should be minus 2. Hopefully you guys noticed that, right? I was flowing this way, so this one was plus the current times this. I'm in the same direction with current, so I get a minus. So for this guy, I do the same thing, 45 minus 41 times I3. So 41, and I am here, I turn around, I come to here, and I got another potential increase. This is going to be 80. And I have minus 1 times I2 and minus 20 times I2. That's going to be minus 21 times I2, which is equal to 0. So I have like, how many unknowns do I have? I have I1, I2, I3, 3 unknowns, and I have 1, 2, 3 equations. Actually, I can form another loop, and maybe you can do this as a homework. Follow this loop and check to see if you get any new conditions. For me, these are enough, right? 3 equations, 3 unknowns. I'll manage with these. So let me do this. So what can we do here? So maybe I can see from here, I3 is equal to, from this equation, I3 is equal to 45 divided by 41 minus 30 divided by 41 times I1. From this guy, I can do the same thing. So, and solve. Actually, it's better to solve for I2, right? Because I can write I3 in terms of I2. I can write I1 in terms of I3, and plug in here and then solve it. But I think it doesn't matter. Let's just keep going. Is it gonna be simpler? So let's do this. So this guy, delete. I1 is equal to 45 divided by 30 minus 41 divided by 30 I3. Good, not that hard at all. And the other one is I2 is equal to 45 plus 80 is 125 divided by 21 minus 41 divided by 21 I3. Good. Now I have something for I1, something for I2. Let's plug these two guys in here and solve it for I3. So this will be, okay, 45 divided by 30 minus 40. Okay, I'm going to just copy it. It's taking time to write these things. Copy, paste, and take this guy here. And this is a plus. This should be equal to I3. Okay, now I3, collect all the I3s together. I have 1 plus 41 divided by 30 plus 41 divided by 21 should be equal to 45 divided by 30 plus 125 divided by 21. So the plus is like this, okay. There are two things, right? The resistor and the battery. And in the resistor, if you are going in the same direction with the current, because my loop is independent of current, right? I could follow my loop like this or like this. But I chose my current to be like this. I mean, I chose my loop to be like this. So my current and the loop are in the same direction. If this is the case, whenever I pass through a resistor, I put a minus, because when you pass through resistor and the current, voltage here should be higher than voltage here. So this minus this is a minus, so you have a minus. And whenever you pass through a battery, you look at the terminals, right? From here to here, you go from lower to higher. So higher minus lower is plus, right? That's a good question. Maybe I can, is that clear? So whenever your current is in the same direction with your loop, I times R is minus, and battery is actually simpler because if you go this way, like this is bigger minus smaller, it is positive. If you go this way, it's like smaller minus bigger, it's negative. I think that rule is the simplest I can keep in my head. You may have other formulas for yourself. Okay, let's calculate this result and see what it is. Okay. 45 divided by 30 plus 125 divided by 21 is something like that. I divide this thing by 1 plus 41 divided by 30 plus 41 divided by 21. And this thing is like, from here, I found I3 to be 1.7 ampere. Now, from this, I can calculate I1. It's given here. Let's do this. Clear is equal to minus 0.8. Turns out I is in the opposite direction, minus 0.8 ampere. And I2 is equal to, so what was it? Clear 125 divided by 21 minus 41 times, what was it? 1.7 divided by 21. And this is equal to 2.6 ampere. Okay. I think, as you know, it would be a miracle if I got these numbers right. So check it. Okay. I probably mess up a lot of things here, but the logic is like this. You have 3 equations, 3 unknowns, eliminate one by one and solve each. It's kind of mechanical, so you don't need to have like some clever idea. Maybe we can solve one more and then we can take a break. Okay, let me just talk about this page and let's take a break after that. So I showed you EMFs are the elements of circuit that provides the current. They are the source. And we can actually connect EMFs in parallel or series too. So we have to be careful with that. For example, we can put one battery after another. Maybe you would like to have like a higher voltage, so that makes sense, right? And then you have like a higher current passing through R. But you could actually connect these in the opposite ways too. You may say, look, why would I do that? Actually, you do this all the time whenever you charge your battery, whenever you charge your phone, right? You do not exactly this, but something like this. You connect the battery in your phone in the reverse direction of a current so that it can be charged. For example, this 20-volt battery here is kind of charging 12-volt battery if this battery is rechargeable. And finally, we could think of like an arrangement in which 2 batteries are connected in parallel. In this case, like voltage is the same, right? And you are providing some current, some total current here or here, right? And here is an example from your book. Maybe, I don't know if you ever had to do this kind of thing, but if you do, I think hopefully this exercise will tell you to be careful. So this is about jump starting a car. A good car battery is being used to jump start a car with a weak battery. Okay, so this is the car which doesn't start. This is your friend's car, and you have your jump cables and you jump start from here. Okay, and there are like some cables, some resistors inside. And the question goes, the good battery has an EMF of 12.5 and the internal resistance of 0.20 ohm. Suppose weak battery has an EMF of 10.1 volt, internal resistance 0.1 ohm. Each copper jumper cable is 3 meter long and 0.5 centimeter in diameter and can be attached as shown here. Assume the starter motor can be represented with a resistor RS 0.15 ohm, this guy, and determine the current through the starter motor A if only the weak battery is connected to it, and B if the good battery is also connected here. I think for simplicity, I'm not going to take this. Let's neglect RJs, okay? These are like 0. Maybe take RJ is equal to 0, and this RJ is equal to 0. I think there will be a little bit difference from your book, but it's okay. I think let's keep it a little simpler, not to deal with a lot of numbers. So what would I do? Maybe I can form, okay, first A is easy, right? Let's start with A. So it's basically saying that you only have the weak battery, so you have this port and nothing else. So I can just calculate some Kirchhoff rule if you like, or if I can do it the way I did in the first page, it's like E minus I times R should be equal to I times RS. And from here, current is equal to E divided by R plus RS, which will be equal to, okay, clear, this is 10.1. This is equal to 40, something like 40. So if only you have the weak battery, that's the current you have, which may not be sufficient to start your car. So you bring the other car and then you connect, and let's see how much it changes, right? If the good battery is also connected, so let's do this. We have to form Kirchhoff circuit. We have to form loops and then apply Kirchhoff laws, right? Luckily, there are like already labels for us in this problem. So let's write this. B, so I1 plus I2, they come here. This guy and this guy, they come here and they meet to I3, so it must be conserved. This is I3. So this is the first one. So let me form a loop like this. So then it is going to be what? So some R1 times I1, and this is minus because I'm in the same direction. And now this one is like bigger minus smaller, so it's going to be positive, so plus 12.5. I ignore the jump resistors, and I have this guy. I'm now going from bigger to smaller, so smaller minus bigger is minus, so it's going to be minus 10.1. And here I am in the opposite direction of the current, so this is also plus. This is plus 0.1 times I2 should be equal to 0. Okay. So let's form another circuit, maybe like this, right? Now it's going to be like what? It's going to be I2 times 0.1. And I'm in the same direction, so I put minus. So now I'm flowing from here. I'm here, bigger minus smaller is going to be plus 10.1. And I'm following here and I'm here. So it's going to be same direction with the current. So it's going to be minus RS times I3 is equal to 0. So we are going to do the same thing. Let's solve I3 is equal to 10.1 divided by RS is like 0.15 minus 0.1 divided by 0.15 I2. And so this is from here. And from the first guy, I can solve I1 in terms of I2. This is going to be I1 is equal to, so 12.5 minus, okay, 12.5 minus 10.1 is equal to 2.4. 2.4 divided by R1, which is equal to 0.02. Okay, I have this guy, I have this guy, and I need to write it in terms of I2. This is equal to plus 0.1 divided by 0.02 I2. Now combine everything in this equation. Okay, this is from that, this is from that. Now put this guy back in here. If I do this, okay, I'm going to do as I did in the previous example, copy these guys and write it here. Paste. Copy this guy. This is 3, 1. Okay. Okay. This one is 3. This one is an equal. And this one is I1 plus this. Okay, good. So I2 plus. Okay. So as you can see now, I have an equation with only one unknown, which is I2, I2, and I2. So let's solve this for I2. So I2 parenthesis, okay, 1 plus 0.1 over 0.15 and plus 0.1 divided by 0.02 should be equal to 10.1 divided by 0.15 minus 2.4 divided by 0.02. So then this will be equal, this will give us, let me calculate this. Okay, this guy is this way, okay. Clear 10.1 divided by 0.15 minus 2.4 divided by 0.02, something like that. And divide this whole thing with some parentheses, 1 plus 0.1 divided by 0.15 plus 0.1 divided by 0.02, close the parenthesis, result is minus, this is I1 is equal to minus 7.9. So we actually want I3. Let's see if I messed up, and let's see if it's going to be bigger. So I3 is equal to, where did I find it? I3 is this, okay, 10.1 divided by 0.15 is going to be plus because of 2 minuses, 0.1 divided by 0.15 times 7.9, which is equal to, clear 10.1 equal to 72. Good. 72.6 ampere, which is obviously larger than 40.4. So you are in good shape. So you can see what happens, right? You have like a weak battery, like you have a small voltage, and then you jump start it and you have like a almost twice as big as of current you had. And that's how your car starts. So I'll give it like 5-minute break, but I want to ask you the following, which may be useful to you. So what happens if you connect this in the opposite way? So this is actually an exercise from your book. If the jumper cables in this example were mistakenly connected in reverse, the positive terminal of each battery would be connected to negative terminal of the other battery. What would be the current even before the starter motor is engaged? And why could this cause batteries to explode? Right? What happens if you connect this side to this side and this side to this side? And forget about this. Let's say you didn't start your engine, you just connected the batteries. And what do you expect? So I think what happens is, like, maybe I can show you here. So this battery will be reversed, or you can think of this battery being reversed. Then there is like a battery like this. This guy comes in, and there is another battery like that that's also in series. You have twice as many volts as you would have, and you would, almost twice as much current. So the current would be flowing this way, but that current would be much bigger than the current that these batteries can carry. So even before you start your car, there will be a huge current passing through this. Of course, when you try to start your car, this current will decrease a little bit, but it's still going to be huge. And I think you should do this homework, and you can see the big current. I mean, huge in terms of these guys. You're going to have like hundreds of amperes. And when you pass such a big current through the batteries, these guys are already dangerous. They become more dangerous. And there's a good chance that it can explode if you do something like that. That's why these cables actually are like marked with colors carefully. Just read them, and then you're going to be in good shape if you ever have to do this.